Welcome to Module 6, where we're going back into networking. This is going to be a module that builds upon the Intro to Networking module that we covered a while back, and it's also going to combine a lot of knowledge that we've learned from everything from Module 1 to Module 5, revisit some concepts, and start layering on the information that you've learned in a more conceptual approach. So we have a couple of sections here. Section 1 is going to be routers and switches again, touch on some more terminology and key ideas to know about these devices. Section 2, we have terminology. 3, a little bit of security concepts as it relates to networking. And then the beast that is Section 4 of subnetting. So let's dive in. Section 1, we have routers and switches again. I just wanted to start off with this slide here, kind of covering some of the industry leaders that are out there for the networking space. Obviously, we have Cisco, Palo Alto, Juniper, Fortinet. I want you to be familiar with some of the leading companies that are out there. Kind of just made a list here to be familiar with them. And then if you're going into a company or an interview and they're kind of talking about their firewalls that they're using, these are kind of like the top 5 industry leaders that are out there. You can have your ASAs, your Cisco ASAs. You could be using Fortinet FortiGate, Palo Alto's, their Panorama firewalls are excellent. You could be using Checkpoint or Sophos. Just wanted to give you some names and key firewalls, technologies that are out there leading the space, that you're not caught off guard with some of these brands and company names being thrown at you at a potential interview. I also wanted to make this slide so that if you like networking and you're thinking of going the network admin route as a first entry-level position, Palo Alto and a lot of these companies as well have free education available to you on their website. As long as you create an account with them, you can kind of go through their on-demand learning, get familiar with some of the technology that they own and their proprietary stuff, get a digital badge, or you can go test for some of the top certifications that are out there related to networking as well. The CCNA certification is one I'm sure you're familiar with. You can also have their network professional certification. CompTIA has their Network Plus, and Juniper Networks also has their Certified Internet Associate. So if you like the route of networking, you think maybe you want to do something with firewalls, and that's where your interest lies, then definitely check out some of these leading companies and see if you like their product. So networks at a high level, we're going to use the Cisco model here to break down all of the different layers. The Cisco model is a hierarchical network design model, and it's broken out into 3 essential layers consisting of access, distribution, and the core backbone that is the internet. So in any network diagram, the internet is always drawn as the cloud. It would be really crazy for us to try and draw every single route option that a packet could take over the internet, so we just kind of blob it in this cloud to say, oh, it's going over the backbone of the internet. So that is layer 1 at the top, the core backbone of the internet. The next layer down at layer 2 is where all of our routers are living. And this is for distribution, routing packets. Layer 3 of the OSI model, the network layer. Routers are handling our logical addresses and doing the distribution for our network. The last layer of the Cisco model is layer 3 for switches. Switches, we're thinking layer 2 of the OSI model, and they're taking their frames and forwarding them off to where they need to go. Maybe we're thinking ARP for address resolution protocol, tracking IP to MAC, and below, kind of what the Cisco model outlines here for a basic network hierarchical structure, saying every network is kind of set up this way. You have your end devices, servers, endpoints, users, etc., that are all kind of accessing your network. So at a high level, the network is always going to have 3 core layers, with number 1 being the backbone of the internet, going down to routers, and then ending up with your switches as the 3rd layer. Speaking of switches, we have a little bit more information to cover with them. These are the 3 main things that a switch does. It's going to do address learning. So it's going to have a MAT contained in it. The MAT is the MAC address table, and the MAT is going to live as a list on the switch, and it's going to map the MAC address to the port that came in on the switch. the switch is going to remember this and map it. So it's going to learn the MAC addresses of all the devices that are connecting to its ports, and remember that that source MAC address on that frame that came in arrived on this port, or this port. And it's going to keep that in the MAC address table. So that's the first part, address learning. The second part is forwarding and filtering. The switch is going to use the information within this MAC to make forwarding and filtering decisions based on the destination MAC that came in from that frame. If the destination MAC is found on the MAT, it's going to forward it off to its destination. If it is not found on this table that the switch is storing, it's going to broadcast it out on all of the ports except for the one that the frame arrived in on. So let's say that the frame came in on this port, the address is not able to be located in the MAT, the switch is not tracking what MAC address is to that port, so it's going to flood out on all of the other ports except for the one that it arrived on to try and map the MAC to that port. So it's keeping track, it's forwarding, it's filtering, and it's doing address learning. The last important thing that it does is avoid loops. It's going to avoid loops by doing spanning tree protocol, STP. I would definitely be familiar with it. We have an entire slide dedicating to breaking this down further on the next slide. But at a high level, it's STP. It's a protocol that's going to run on the switch to prevent loops from occurring in the network. It's going to elect the root bridge and establish essentially a loop-free topology for all of the switches to communicate all of their frames with each other. It's going to consistently monitor the network topology and adjust if a forwarding path fails, or if a link goes bad, or if it's possible degradation to the switch and how it functions. So again, switches, we're building on our terminology here. We're thinking OSI model layer 2 for data link. We're thinking MAC, our 48-bit MAC address, that is our physical address. We're thinking address resolution protocol. We're thinking frames is the PDU name. And now we're thinking it has a MAT table, the MAC address table, which is keeping track of our MACs to ports that are coming in on the switch. And now we're also thinking spanning tree protocol to prevent loops. So we're just building on top of the things that we already have discussed and introducing just a couple more to get a little bit more in-depth familiarity with switches. Breaking down spanning tree protocol a little bit more, at a high level, if you just remember loop avoidance for switches, I think that's a great response to any potential interview question that you could get. Do you need to memorize that there's going to be a root bridge elected and it's going to do mathematical algorithms and it always detect the best path for the frames to take? No. But at a high level, we need to understand that it's a protocol used by switches to prevent loops in the network, and it's going to create a loop-free topology, and it's going to identify any kind of redundant links and block them by using a block port to not have the loop ever be created. So STP is going to elect a root bridge. The root bridge will have root ports that run on the other switches, and the root bridge will detect and allocate designated ports for the frames to be sent forward and back through the switch's communication. And it's going to elect these destination ports based on the best path for all of the frames to take, and considering it doesn't want to create any loops. So if a link or switch in the network fails, STP is automatically going to recalculate the topology and adjust the forwarding path accordingly to ensure the network remains loop-free. And BDPU messages is actually what's sending out these spanning messages, and BPDU stands for Bridge Protocol Data Units, and that's actually what's sending out the spanning messages here. So I just wanted to define that for you guys there. And a good analogy for what STP is doing, any modern switch is going to have this protocol enabled on it. But if we think about it as a car trying to drive around a roundabout endlessly and it never gets off the roundabout in the road, well, if there are other cars that are trying to get into the roundabout and they can't because this car is just stuck in a loop, your network is going to become degraded. Your switches are not going to be able to forward off any additional frames because this frame that's in the loop is taking up all of the traffic. So STP is going to prevent any kind of frame or car in this analogy to keep going endlessly in a loop. So hopefully that analogy helps. At a high level, remember, we're just thinking loop avoidance for switches. It's a protocol that any modern switch is going to have. And if you want it to be extra fancy in your knowledge for what it is, you can say a root bridge is elected. That's going to calculate the shortest path from each switch, and it will have designated ports and root ports and blocked ports to ensure that the best path forward for the frame is taken. And how it recalculates the topology is by sending out the bridge protocol data units, which is actually the spanning messages, to ensure that topology is correct and has the best forwarding paths for the network. Okay, routing tables. We just talked about switches, so now we're thinking routers. We're thinking OSI, layer 3. We're thinking logical addresses, and we're thinking 32-bit IP address. We're thinking IP version 4, IP version 6. We're thinking WAN to WAN connectivity. That's kind of the buzzwords that are coming to mind here. The only terminology that we're adding on top of this now is the concept of static and dynamic. But first, let's cover what a route table is. A route table is going to look similar to this, and it's going to be a list of entries stored on the router that's going to tell the router where to forward packets that it receives. So here we have our network destination. These are our active routes in our route table. This is the network mask, which we'll cover in a few slides later. We have our gateway for telling it where to go, what interface it's on, etc. So each entry in the routing table is going to contain information about the destination network, where's the next hop for the next router to take, where am I going next, which is the IP address for the next router or destination where the packet should be sent. So this is all the routes that the router knows, and that's been put in there. Or, well, if it's put in there, it's static. You can have two types of routing. You can have static routing, which in this diagram kind of depicts it's manual, and it's not going to divert to take any other path because it's learned the route statically. It's been statically assigned to say, always go from A to B to C to D. Don't learn anything else. This is static. This is where I've told you to route it, and that's how it's been assigned. The other type of routing you can have is dynamic. So these are going to be learned by the router. They're not going to be put manually into the router for the path to be given to it. It's going to be able to take whatever path it wants to get to its destination, and it's going to be learned automatically by the router through a routing protocol. So you can have OSPF, that is open shortest path first, or BGP. BGP is Border Gateway Protocol, and these are two main routing protocols that make routing destinations across the internet. They're both using dynamic routing, and it's just however the network is set up, they can use one of those routing protocols. And the routers are going to exchange information with each other to dynamically build and maintain the routing table. So these are all going to be working together to remember the path of routing to get from point A to point B and all of the options in between. It's dynamic. It can change. It's learning and evolving. Whereas static, it's been manually put in. It only knows A, B, C, D, and if C goes down, the packet's not going to get there. It will fail. So at a high level, routing tables, it's just a table for a directory that tells the router where to forward the packets off or where it receives. Where is that next hop going to be? And then for routing, you can have static or dynamic allocation. Access control lists is definitely a terminology we want to be familiar with. This, we're thinking firewalls, we're thinking rules, and the most important thing to remember with ACLs is the implicit denial statement that's always at the bottom, which we will get to in a second. But basically, an ACL is an access control list. This basically says who's allowed in, who's not allowed in, what IP is allowed to come in on what traffic, or what traffic based on protocol do we want to allow or deny. It's access to resources on a network by permitting or denying the traffic, again, based on source or destination IP addresses, protocol types, port numbers, etc. They can be configured as standard or extended and operate on an inbound, outbound traffic on an interface. They help to protect against various types of attacks and are an important tool for network security. You should definitely be familiar with ACLs, what ACLs are, why we have them, and that they're found on the routers. So this is a sample of what an ACL could look like. We have our name of the list. It's called access list. And what access lists are we referring to? Well, we're adding all these rules to access list number 101. And then you have a statement here that's like permit to allow or deny to not allow. You have your protocol, TCP, UDP, ICMP, etc. You have your source IP address followed by the source IP's network mask, which we will cover. Then you have your destination IP followed by that destination IP's network mask, and then equals, protocol of telnet. You can do FTP, HTTP, echo reply. Looks like we have some web rules down here. This is a basic ACL. It's saying allow or deny based on these criteria of IP addresses or protocols, and it's going to read it top down. That is an important concept to remember for ACLs. As the frame or as the packet comes into the network, and let's say this is the packet, as it comes into your network, it's going to hit your firewall, and when it hits your ACL list, it's going to say, the router is going to say, does this packet meet this criteria? No. So let's allow it to go to the next rule that we have in place. Does this next rule in place prevent that packet from coming in? No. We can go to the next one. If the packet makes it through all of these checks and rules that's in there to say it can go in, or if it's being denied, it will make it to the bottom. And what is always at the bottom is the implicit deny all packets. So it's going to be a deny all or deny any for any IP address, any protocol, any port, etc. Deny everything else. ACLs usually work in a whitelist format. So all of these rules would be all for permit or allow through, because it's easier to write a whitelist ACL to say this is the only traffic that I want coming into my network than it is to try and think of every single possible combination out there for everything you would want to blacklist. So pretty much if you write it where I'm only making rules for traffic I want to allow in, and then everything else I'm going to deny from coming into our network, that is usually how they are written. But you can obviously write them to have a combination of permit or deny. That's just an example of how I've seen them be written and how they probably should be written. As the whitelist, if the packet comes in and it doesn't pass any of the whitelist approval for the criteria set, then it's going to be denied and dropped off because that's not traffic that we're wanting to work with. So access control lists at a high level, we're thinking firewalls, we're thinking a list that's read from top down as the packet comes in to say, is this criteria something that our network has said is okay? If so, it's going to match on one of the rules within the whitelist, and then if not, we're denying all. We have our implicit denial statement as the last rule to drop the packet. So an introduction to ACLs, I would definitely be familiar with the term and why we have them and what they're used for.